So let's talk about the standard Gaussian integral. This is called the standard Gaussian integral, and this is some kind of integral we call non-elementary. That means you can solve this integral with normal integral techniques like U substitution, trigonometric substitution, or integration by parts. You have to use some special techniques. So first we're gonna name it I. First, I want to talk about where you are going to use this integral. This is inevitable to encounter in statistics, so-called normal distribution. Let's back to the solution. We'll rename it as I. What if we square this I? We'll just get it times x. Here you can see one thing that these two are the same things, and even if we change the variable of any function in any integral, until we change its formation, the integral remains the same. So we're going to do this. We're going to remove the x here and replace with y, and again replace with y. And here's another thing. We can use a double integral here. These two integrals make a double integral, e to the negative x squared times e to the negative y squared dx dy. Here we can add these two things. We'll just get negative x squared plus y squared dx dy. Here you can see something. This is the equation of a circle, at least in one side. We know that equation of circle is r squared equals x squared plus y squared. So it has obviously a connection to the circles, and circles are easier to deal with in polar coordinates rather than Cartesian coordinates. We're going to do the same thing here. We're going to convert this integral into a polar integral rather than a normal integral in Cartesian coordinates. So let's rewrite this. X squared plus y squared dx dy. And in our polar coordinates, the x squared and y squared is given as the r squared. In polar, we only care about from this origin to this point and its distance r and this angle theta. And this point is denoted as r comma theta. This is all we care about in Cartesian in polar coordinates, and in Cartesian coordinates we care about x and y's. So we're gonna write it as negative infinity, 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 e to the negative r squared. This negative remains here. And see, we cannot deal with dx and dy anymore. We have to deal with dr and d theta in order to integrate this in polars. Dr, d theta. But every transformation comes in a cost. Here you can see the dx and dy term is actually representing an area. Here the dr and d theta is also an area. Area to area, we are going to use transformation. First, I'm going to give you a simple example. If you have an area A and you are changing it by dividing 2 and you get B. you want to write b in terms of a, that these two remains the same. So this will be just a equals 2b. Here you have to add multiply a constant. And what's the constant here? We know that determinants just mean this constant, by which factor an area changes. So we have to take the determinant of something. But whose determinant we're going to take? Here comes the important part, which we're going to call, this is called the Jacobian matrix in terms of x, y, and d, and r and theta, which is denoted as del x, del r, del x, del theta, del y, del r, del y, del theta. And we're going to find the determinant of these. Again, we have to look at the polar equations. In polar, x is written as r cosine theta and y is given as r sine theta. So we're going to rewrite this x and y in terms of this equation. The partial derivative of x in terms of r is just cosine theta. Partial derivative of x in terms of theta is just negative r sine theta. Partial derivative of y in terms of r is just sine theta. And partial derivative of y in terms of theta is just r cosine theta. And we know the determinant of a 2 by 2 matrix is given as the multiplication of these minus this times this. So this can be written as r cosine theta times cosine theta minus sine theta times negative r sine theta. Here you can see this negative and this negative are going to cancel out and gives a positive. Right here. So we're going to get r cosine square theta minus plus r sine square theta. Here we can factor out r and just will remain as cosine square theta plus sine square theta. From basic trigonometric equation, we can clearly see that this is just 1. So we are left with r. So this integral changes with a factor of r, and we are going to write this r here. Here goes all the hard parts of this integral. But as we convert it into polars, these boundaries are not going to work. Negative infinity to positive infinity just means we have to integrate all over the surface. And this theta is negative infinity to positive infinity. But in polar coordinates, angle starts from 0. And the highest you can go is 2 pi. In radians is 2 pi, but in angles or degrees, you will just get 360 degrees, which is the same as the angle of a circle. And here you can see the dr term. R just starts from 0 and go up to any values or infinity. So this is from 0 to infinity. Now you can easily integrate this. We have to use a u substitution, normal u substitution here. We can substitute r squared as u. Let's say u equals r squared. So we're going to get du equals 2r dr. Let's rewrite it. 0 to 2 pi times 0 to infinity e to the negative u, as r squared is just u, times r times dr is given as du by 2r. So du by 2r. Here you can clearly see that this r and this r is going to cancel out, and we're left with 1 half e to the negative u. And lastly, d theta. As d theta, as 1 half is a constant, we're not going to write this. We'll just get it outside the integrals. 0 to 2 pi, equals of 0 to infinity e to the negative u du d theta. The integral of e to the negative u is just 1 half 0 to 2 pi negative e to the u e to the negative u from 0 to infinity. Here's our bound 0 to 2 pi, 0 to infinity times d theta. We'll have to evaluate this value. E to the negative e to the negative u from 0 to infinity is given as e to the negative infinity minus e to the negative 0, also 0. Here you can clearly see that this negative and this negative will just leave us with the positive sign. And from the limit, we know that something to the power negative infinity will just give us 0 plus something to the power 0. As long as it's not 0, we're gonna get 1, and we're left with just 1. Now this is gonna get a lot easier to evaluate. So 1 half 0 to 2 pi, and this integral is just 1 d theta. Here we have left with 1 half, and the integral of 1 in terms of theta is just theta evaluated from 0 to 2 pi. And if we evaluate it in terms of 0 and 2 pi, we're going to left with half theta equals 2 pi minus theta equals 0. So we are going to get 1 half times 2 pi. This 1 half and 2 cancelled out. We're just left with the pi. Some of you might wonder what pi is doing here. Pi just came from the angle. That is why this absurd integral's value is just pi. But that's not our answer. That's not our Gaussian integral's answer. Remember, we squared this value and find pi. And if we are going to take the square root of both sides, we're going to see that I equals root over pi. So our final answer is from negative infinity to positive infinity, e to the x squared dx is just root over pi. This absurd looking integral is going to help us a lot in statistical mechanics and normal distribution especially. This is what the answer. It's surely very absurd to get pi where there is no pi, just full of x's and infinities. That was all for today.